All right, so moving that into the overall sequences. Now that I'm supplying my supplier, I figured out my supplier, my optimum supplier temperature. Now I have to maintain it. So how do I maintain it? It starts out with the cooling. If my maximum load, I'm up here. As the supplier temperature control loop signal goes down, I start reducing the cooling coil. Then I start reducing the return air damper. Then I start reducing the outside air damper. And then I start opening up the hot water valve. So it's all in sequence. And it's all done with one control loop. And this allows you to ensure that you're never heating, that you don't have the economizer and the heating coil at the same time, the chill water coil and the economizer at the same time. It guarantees you that. Now, all of these different things have different gains in there, so you can change the gain of the PID loop depending on if you're over here, it might be one gain. If you're over here with the dampers, it might be another gain. And with the hot water coil, it might be another gain. So the gains can be changed so that you can adjust for the sort of the dynamics of the different different valves and stuff. And then on top of that is the economizer controls. So we have these variables, max OAP, max RAP, and these are numbers that are a function of the economizer. So right now it assumes that the economizer, it's showing the economizer as being wide open. There's another logic that turns it off, right? That says, oh, it's not good for economizing anymore, and it'll make max OAP 0. And then, or no, it makes it equal to min OAP if it's controlling minimum outside air. And the same with the return air damper logic. It has a controlling loop based on ventilation. One of the things people don't quite understand is that ventilation is actually controlled, in most VAV system, is controlled by the return damper, not the outside air damper. Because when the pressure goes down in the VAV mixed air plenum, sometimes I gotta have the outside air damper wide open, and I'm not getting enough outside air because the pressure is so low. So I have to throttle return damper to create a pressure to pull the air in. So that's all built into these sequences. Here's an interesting one with return fans. It looks almost the same, but look at the outside air damper. It's all wide open. So this was part of another research project that created Guideline 13. And in that one, somebody realized that you don't need to do anything with the outside air damper because the return fan is blowing the return air into the mixed air plenum. And so supply fan's delivering what the supply air is. The return fan is blowing the outside air. What's left over is outside air. And it doesn't matter whether the damper's open, closed, or anything else, you're going to get the same outside air if you're controlling all these things with the damper wide open or not. So you don't even need a damper other than when the system turns off and you want it to be closed when it's off. So very interesting change there. And of course, this saves energy too, because now that damper is wide open and you don't have any pressure drop across the outside air damper. We're doing a laboratory right now that has the building is about half lab, half office, and we have a return fan, and we don't have any outside air damper at all because it runs 24/7, and the ventilation requirement, because of all the labs and all the 100% outside air stuff, is way more than what the offices need. So I don't even have to measure the outside air. I'm always over-ventilating the building. By using one air handler for both the labs and the offices, I'm actually sort of using the ventilation air from the labs to ventilate the offices for free, so to speak. And the controls are super simple. I don't have any. So I have no outside air damper at all, and no airflow measuring station because I know I'm always ventilating more than I need to. So it's quite pretty. So economizer high limit lockout. We all know that at some point you've got to turn off the economizer because the outside air conditions aren't right for free cooling. A lot of people wanted that you, as the designer, would have to say, what kind of logic you wanted to do, what the set points needed to be. And I said, no, I see this too often. People don't do it right. So instead, Guideline 36 says, what climate zone are you in? Okay, and if you're either an ASHRAE climate zone or a Title 24 climate zone. And then it builds in the tables in here internally. It's part of the control logic, so you can't change the number. You have to use what Title 24 and what Standard 90 says
for the shutoff. You just say what climate zone you're in, and it does it for you automatically. And that way you can't screw it up. This is for 90.1, and it has 4 different kinds of ways of turning off the economizer, and that tells you which zones you can use them in. And if you have ones that have fixed set points, it tells you what those set points have to be. All these came from simulations for sort of a typical office. So they're not perfect, but they're pretty good. And they'll give you the right number. The reason why these vary, these are the dry climates up here, and you want to turn it off when the outside air temperature is 75. In the humid climates, you turn it off at lower ones because of humidity. So you're going to get more humid air in there. You'll notice that differential enthalpy and fixed enthalpy are not allowed by themselves anymore. You always have to put a dry bulb sensor on top of them as well. And the reason why is because they're inaccurate. Measuring humidity is a difficult thing to do accurately unless you maintain your sensors really well. California actually doesn't even allow differential enthalpy at all. It's not allowed at all because it's so bad. So the errors on the thing. So when you think about differential enthalpy, I got to measure return air, return humidity, outside air, outside humidity. So I got 4 variables, all of which can have error. And the humidity ones often have 100% error or 50% error. You know, they're terrible. And so it just really doesn't do you any good at all. But anyway, this is all built in. So the engineer would just say, or the controls person would say, I'm in climate zone 3C, that's California. And I want to use both a differential dry bulb and fixed dry bulb. You can do combinations if you want. So I'm going to do both of these, and it will automatically do it. All right, now I'm going to go on to static pressure set point reset and the trim and respond in more detail. So again, we have a pressure sensor out in the system. Of course, probably everybody knows the rule of thumb, right? It's 2/3 of the way out into the system. Literally nobody knows where that came from. It's been a rule of thumb that for years. I've gone back in some of the old textbooks from the 50s and stuff. It was there even then, even though they barely had VAV. But nobody knows where it came from. But the real answer is it should be as far out as the system as it could possibly be. But when you do static pressure set point reset, it doesn't actually matter where the sensor is. We still put it out in the system pretty far because in case the building engineer disables the reset capabilities. But if you're doing static pressure set point reset the way we describe it here, it doesn't really matter where that sensor is. And it doesn't have to be calibrated, and it doesn't matter. It doesn't matter what it's measuring because we're resetting it. Oops. Okay, so trim and respond. I mentioned this earlier as a way of trying to do a dynamic reset. And we use it for static pressure here I'm going to describe. We use it for supply air temperature. We use it for chilled water and hot water temperature reset. The way it works is that zones will generate a request. For supply air temperature reset, it's the cooling loop. As the cooling loop, as it goes up to 100% or so, 95%, it'll say, I want colder air. For static pressure, when that damper loop gets almost all the way open, it'll say, I want more static. But then when it drops down a little bit, it'll say, oh, no, I'm fine anymore. I don't need anything. Part of the reason for all this being at the zone level is that it doesn't require polling. So another way of doing static pressure set point reset is to say, what's the damper position in every zone? And I'm going to try to keep one of those dampers wide open. But that requires it to go, what's your damper? What's your damper? What's your damper? What's your damper? And a lot of networks, particularly LAN networks that are really slow, but even MSTP, can't handle that. They can't handle all that traffic. So the way requests work, it's all at the zone level, and it only puts traffic up there when it wants something. So if it says, I want static, that's the only thing that goes over the network. All of our logic is built that way. It's all zone up. So the zones tell the air handlers what to do. The air handlers tell the plant what to do. Nothing runs like the air handlers have no schedules. The schedules are all reside in the zones, so in the zone groups. All right, so I generate a request. Oops. When I exceed some amount, and then I drop off the request later. And then we can, one of the powerful things about the trim and respond idea is that we can put importance multipliers on the zones. So if you have a importance multiplier of 0, it means I don't care what you want. I'm not going to make the whole system deal with what your irresponsible request is. Now, where might you use this thing? Well, we get this in two situations. One is sometimes you have people that really like their offices cold. And if I can do it for free, fine, But I'm not going to run the supply air temperature down to 55 in the wintertime just because that person wants it cold. So you give them a 0, and that way they can't wag the dog, but they can get it when the system can give it to them. So that's one example. Another example is we often cool IT closets with both a VAV box and a split. And the split is just for off hours and whatever, but it's more efficient to cool it with a VAV system with an economizer. And sometimes IT guys think that computers like to be cold, and they don't. But they don't believe that. And so we say, fine, you can make the set point whatever you want, but we're not going to make the system deliver that. So, and of course, you always have your split that can turn on at some point anyway. So those are the kind of reasons for doing IM equals 0. You can also just do it. Some building engineers, just there's some people that annoy them or something, and they give them 0 just for fun. The default is 1. And then you can also do greater than 1. And so this would be a zone that's super important and that you don't want to ever ignore them. So in a minute, I'll talk about the ignores. So when you're doing the reset, you can set any number of ignores you want, which means that I'm not going to start resetting with just one zone wants something. I want at least 3 zones that want colder air before I'm going to make it colder. So, but if this zone was really important, you could give it a multiplier of 4. And that allows it to jump over the ignores and says, OK, well, you're important. You can get everything. All right, so once we get the request, we multiply it by the importance multiplier. We send it to the controller at the air handler. So what the controller will do is it has a little time cycle that says every minute, every whatever, I'm going to, in this case, I'm going to drop the static pressure set point. I'm going to drop it, I'm going to drop it, and drop it until somebody requests, and enough to get past the ignores. And then if they do, then I respond. So I'm trim, 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 respond, trim, trim, trim. So it looks like this with static pressure requests. So here's the request down at the bottom, number of requests. I have 2 ignores, so I'm going to ignore the first 2 requests. And then here's the static pressure set point. So it's saying, OK, there's no requests, so I'm going to trim. Time cycle again, I'm going to trim again. So the red is the set point, and the green is the actual with the fan tracking the set point change. Now when I get to here, the number of requests goes to 3. And so I'm beyond the ignores, so I'm going to respond. Oh, and then I got another zone, so I'm going to respond a little bit more. Then all of a sudden, hey, everybody's happy. Trim, 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 trim. And then somebody's not. Respond, trim, respond. OK, so that's how it works. It's constantly going down. Now, you'll see that it's cyclical. And there doesn't seem to be any way of getting rid of that. We did another research project to try to see if we could do some feed-forward kind of stuff to make it so that it just didn't go up and down so much. Because a lot of building engineers don't like that. And you certainly want to make the time cycle on this thing. Like here's, it peaks at 12:12, and here's at 1:42, it peaks again. So that's a pretty broad range of you want to make sure that it isn't going up and down really quickly, or the building engineer will turn it off in seconds, as well he should if it's bouncing around. So you make it sort of broad to make that go away. We're trying to contemplate a whole different way of doing this that maybe gets rid of this problem, but so far this is the best we can do. We'll probably end up getting into model-based control sequences where we're actually doing a model of the distribution system to see if we can make it better. So here's some real data from one of my projects. And the balancing guy said we need 1.25 inches of static at the bottom of the shaft in this particular case to make all the VAV box happy. We ran this trend thing over a couple of months. And what we found is we never got anywhere near the 1.25. And most of the time, we were way down in here. And in this particular case, I put a minimum of 0.15 on the trim and respond block, so it never could go below 0.15. Now I put 0.05. There's no minimum that you can't be too low, Because if it's so low that somebody wants more static, it bumps up automatically, you know. So I had it artificially low, and it's like wasting some energy there. So no need to make it do that. Let it go all the way down. So you can see that most of the time we're doing 0.15. So this is amazing. So you've got this whole building, and all the zones are perfectly happy with 0.15 inches of static pressure instead of the 1.25 that if we used conventional logic that you'd be at. The energy savings are quite substantial. By the way, we often use these plot where you pack actual versus the set point on top of each other to see if loops are tuned well. And you wouldn't think, like, this doesn't look all that tuned, but it actually is pretty good because you usually tune it way up here, you know, design conditions. And then as you get to less design condition, it doesn't stay in tune as well. But that's okay. I mean, it's reasonably close. We accepted this. It's close enough. That's another thing we could do better is automatic loop tuning. Unfortunately, several companies have patents on automatic loop tuning, and so ASHRAE isn't allowed to do a research project to find out ways of doing it and giving it to everybody until those patents run out. All right, so why is this important? Because the fan energy, percent kW versus percent CFM, is a function of what that set point is. The lower the set point is, the more energy I'm going to save. So perfect static pressure set point reset would be this curve down here where the static pressure set point is 0, meaning that if I had 0 CFM, I need 0 static. You know, and of course in real life you're not going to get to that perfection, but that's basically what you're striving for. The 2/3 of the way down the duct system idea would be this dark blue line, which is pretty good too. You know, and you say, well, geez, that's not much difference between that one and that one. Well, it actually is a lot of difference because this is where we usually reside. With all of our low minimums and our dual max logic, most buildings will, their average CFM will be below 40% for the year, and some even lower than that. And we haven't even tried on some of our ones with TAV now, might even be lower than that. So you're way down in here, and if you look in here, this is like double the energy, right? This is not trivial if this is where your average is for the year. And in fact, our studies have shown that static pressure reset saves about 35 to 50% of your fan energy. So we'll go over to the lab after this. It's going too long. We'll show you a little demo just to show you how good that is. One of the things that it's not quite reflected in here, but we'll see it when we go over there, is when we get down in here, you see how this line sort of flattens out? In real life, it truly flattens out. Below about 20% speed, the kW is about the same, and we'll see that when we go in the lab. And the reason for that is, you know, doesn't the cube law is not working anymore? Yeah, no, the cube law is still working, but the motor efficiency and the VFD efficiency get worse as their load goes down. And the two tend to compensate each other, and so it tends to flatten this thing out right in here. So it means that below about 20% speed, there's not much value in going slower than that from an energy perspective. But there is from a controllability perspective. So the less pressure that the VAV box dampers have to see, or pumps or whatever, the less pressure they see, the better they control. So it's still better to go down to low speeds, even still. All right, so our bad guys are these rogue zones. These are the zones that there's something wrong with them. And they're always saying, I want colder air, or I want more static. And they screw up everything. And what happens is that there's always a zone that wants it, depending on what you set the ignores to. That person can drive the bus, you know, can wag the dog. And it destroys all the efficiency savings of static pressure set point and supplier temperature reset. So how did that happen? Sometimes the load is larger than anticipated in the design. You'll notice I don't say that the engineer undersized the zone. We never undersize anything. We size it perfectly, but if there's too much load in there that they didn't tell us about, that's not our fault. And then there's poor duct design and construction. This is usually also a contractor problem, not a designer problem. Actually, one of mine was definitely a designer problem. I had a VAV box that crossed a rated wall,
and at we had a code exception that allowed me not to put a fire smoke damper in it, but the code guide on the field disagreed with my interpretation of the code, and we had to put a fire smoke damper in it. Well, it was a 6-inch duct upstream of a VAV box, so it's the little tiny duct that's going into a VAV box. And for most of you who do design work, you know, the friction rate of a duct going into the VAV box is quite high. And when you put a 6-inch fire smoke damper in it, which is 8-inch square fire smoke damper, it only has about a ½ an inch of free area because you got the flange around the damper and everything like that. And so that poor little fire smoke damper meant that the chef whose office that was always demanding static pressure. So we had to fix it in the field. Extreme set point adjustments. This could be that person who wants their office always cold, or you can just have something broken. So what happens with the rogue zones? They reset the extremes. We don't want that. Once identified, and we have techniques for helping you identify them, then you can do what? You can repair them. That would be the best thing to do. Or you can lock them out of trim and respond if they're not critical. You know, with that chef in there who was fairly critical, we locked him out for a while until we finally fixed the problem because we didn't want to drag down the whole building for that. But if you feel comfortable doing that, you can set the importance multiplier to 0. When we first did this at a Stanford project, the Stanford facilities people said, just make it automatic. If we detect them to be a rogue zone, they're automatically 0. You know, and they said, I'm not going to do that. You can do that. I'm not going to do that as the design engineer. But so they actually have the logic do that. So it's like, we're not going to let you students be dragged down the whole building. Okay. So I'm not going to read all this, but I'll just summarize what it means. In order to detect a rogue zone, we want to know how often they're requesting. So we create this thing called cumulative percent request hours. So we basically integrate over time the number of requests you have and divide by the number of hours that the system was operating. And that's your percent of time that the system was operating that you're requesting. And we keep track of that, and we display it. So this is a VAV box graphic that we always do in our projects. Some people don't do these summary tables. When it means that if you want to see what all your VAV boxes are doing, you have to click on every single one of them, and then you sort of forget what the other one was before you get to the last one. We really like these tables where you can see everything in one fell swoop. So here's a case where we're looking at the static pressure requests. In this particular case, nobody's requesting when I did this screenshot. Here's the percent request hours over time. And if you get above so much, like 70%, whatever you want to set, you can make an alarm go off and say, hey, this guy is a rogue zone. And you can see in this building, everything's well behaved here. Everybody is requesting at some point, which is good. You know, you want everybody to sort of be requesting. It means you designed the system well. But you don't want them to be a rogue zone. Also on the screen is the importance multiplier. So right there, the building engineer can click on it and make it a 0, or click on it and make it a 3, whatever they want to do with that particular zone. Off to the right is not on the screenshot, was the supplier temperature reset trim and respond data, were requests from the cooling loop. This is the request from the static pressure loop. All right. So those are just a flavor of the logic. And we'll go over to the lab and play with the static pressure trim and respond one for fun. But I want to talk a little bit about how we're going to get there. And I think you guys can be a big part of making this Guideline 36 work. We have a little bit of a chicken and egg thing here happening. The engineers don't want to specify it because they're afraid the entire cost of implementing all these very complicated sequences. By the way, they are very complicated sequences. But again, this is the issue of if you only have to program it once and it's debugged once and it's universal, who cares if it's complicated, right? It's only complicated if it's a one-off thing and you don't get it right. But if we have everybody doing it, it's like our iPhone. It works underneath, and that's what we want. So the engineers don't want to specify because they don't want the cost to be on their job. The local dealers aren't going to do it unless their engineers specify it. And then the manufacturers say, well, I'm not going to do it until my dealers want it. So you have this circular thing, that nobody is doing it yet very, very much. So in my mind, the key is the manufacturers.
first of all, they have the resources. They have lots of money. And we have been trying to get the manufacturers to do the programming for their dealers even before the dealers start asking for it. And in California now, we're doing a research project funded by the CEC where we've got 6 buildings, 4 different manufacturers, and in one case, the manufacturer of the controls has volunteered to do all the programming for the project and then share it with all their dealers. And the other ones, I mean, it's a tough industry. The controls industry is very tight margin, and the controls company said, no, let the local dealer do it. And we're paying the local dealer to do it with the understanding that they will donate it to their mothership and so that everybody can share in these things. But that was the idea of the CEC funding, was to get the ball rolling. Because once, again, it's a win-win-win-win kind of thing. So once you get it rolling, it should be an easy sell. But we got to get those sequences done first. From an engineer standpoint, though, we don't have to wait for anything. Just start specifying it, and the more times people specify it, the more pretty soon everybody has to do it, right? We're all saying use these sequences, then everybody has to do it. There's no choice in the matter. And I think you guys, if you get involved with it and start teaching your techs about these sequences and helping sell it, that can make it happen too. There's 3 ways of actually implementing things if you're a consulting engineer. One is you can take the sequences from the guideline verbatim and cut them, paste them into your specs, and then edit them for the job. Advantages of this are that you get the desired sequences you want, including any edits that may need to be done for that particular job. Another side benefit is the engineer has to read the sequences and thereby understand what's going on, which is a nice side benefit as well, trying to understand what's underneath the hood. But the cons are Guideline 36 isn't yet available in Word format. This is a frustrating thing dealing with bureaucracies. There's a PDF out there, right? And you can cut and paste that PDF all you want. So I told ASHRAE, you already have it out there. And it says on there, you can cut and paste all you want. Let's just give them a Word version so that you don't have to reformat all the thing and all that kind of stuff. They say, oh no, we can't do that. So I want to sneak one out there so one of these days, say, I'm sorry. And then there's a lot of time editing, and it's very prone to error. So when you get it, if you ever get the guideline, please do, and you read it, there's a whole bunch of this. Like if you're using Title 24 ventilation requirements, use the next 3 paragraphs. And if you're using 62.1, use the next 2 paragraphs. And if you start editing things, you lose the fact of the 1 and the 2. It's like, did I delete 2 or delete 1? So it gets very complicated in terms of editing and easy to make an error. And then most engineers are going to do what they do with their master specs, which is they publish the whole master spec and don't even edit it, right? How many people, if you've ever been a contractor, you see that, right? You get a pump spec and it has 25 different kinds of pumps and there's only 1 pump on the job, because they were too lazy to edit the spec. Well, they'll do that with the sequences too. Just publish the whole friggin' thing. We have 5 different versions of dual duct logic, right, and the guideline for the various flavors of dual duct, and they'll publish all 5, and then you don't know if they change something. So if I'm the dealer and the engineer takes the spec and pastes it in and then decides it wants to do something different, how does the dealer know? They already have the stuff pre-programmed. How do they know that they're supposed to tweak this section? It'd be really difficult for them to know that. So there's disadvantages there. Here's another approach where you just say, use Guideline 36, Section 5.6, and I'm not going to repeat the whole thing because you can go get it out of Guideline 36. This is what we do. So our master spec is written this way. It just says, use this particular one. But you still need to have the English language all compiled because the building engineer needs that, right? And the commissioning person. So we put it on the building engineer, the contractor, to take all of the sequences from Guideline 36 and paste them back together again so that you can have the as-built control sequences. So we're sort of shifting that burden. So it's easier for the engineer. The changes to the guideline are very clear. So you'll say like, fully comply with this except, and then you can say whatever exceptions you want. It includes addenda inherently, because you just say use guideline 36, whatever the latest one is. The cons are the burden of compiling the as-built sequences is shift to the dealer, and that is something that they're not going to like too much. Now, having said all that, we have another research project that's federally funded through Lawrence Berkeley Labs, and this is developing a front end to Guideline 36 that allow you to, anybody use Control Spec Builder, CTRL Spec Builder? Yeah, super great software. And so you say I have an air handler, it has a heating coil, has a cooling coil, it has a variable speed drive, got an economizer, blah, blah, blah. And then you say go, and it collects all the sequences. In that case, it does the diagrams as well. So we're doing a research project to do that with Guideline 36, funded by the feds, so that you as an engineer would say, I have an air handler with return fan and a blah, 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 and you just click it all, and then it will compile the sequences for you. Now, the manufacturers often do this already with their actual software. So part of that federal one, I'm digressing a bit, but we're creating a programming language called CDL, Control Description Language, and it's supposed to be like a universal, what's that operating system that everybody uses that it's universal? That's yeah, Linux, yeah. So it's like Linux for controls. And the idea is that it's open source, everybody can work with it, is that eventually we'll put the Guideline 36 sequences in that language, and then manufacturers would simply have an interpreter that converts CDL to ICON or whatever their programming language is, and then they don't even have to write the sequences. We'll just do it as part of developing Guideline 36. So we're a little off from that, but that's the long-term goal of these things. All right, number 3 is you can just say, use the Guideline 36 sequences. Don't say anything more. Easiest for the engineer, for sure. Cons are you can't really change the sequences because you just said use all the sequences. So if you had some special case, you'd have a hard time articulating that. But frankly, the sequences are pretty damn comprehensive, so you don't really have to worry about that much. You're going to get some RFIs because in the guideline there's some choices. So I can control return fans one of 2 different ways. We have a third way coming up. And the controls contractor will say, well, you didn't say which way you want to control the return fan. Which way do you want? And you say, well, that doesn't matter, right? I mean, it's an RFI, and you just say, OK, we'll use that way. And then again, the burden of compiling the as-built sequences are shifted to the dealer. Hopefully when they get that tool going, that's not going to be a burden on anybody. So those are the 3 ways of doing it. And I encourage engineers to just start doing it. If we all start doing it, then the whole thing will develop. So how well does this stuff work? Part of that Energy Commission project where we're implementing it in 6 buildings, we have done 2 of the buildings, and this is controls only. We didn't put any VAV or variable speed drives. We didn't put any hardware in. Literally controls only. And the first building, here's the pre-retrofit range of electricity. Here's the pre-retrofit range of gas over here. And here's the next year. So the gas bill went down in half. That's pretty significant when you're just talking sequences. Here's another one. In this one, we created a regression that tried to predict what the building would do over the next period. So we implemented the sequences right here. We had a regression to predict what it would have done before the sequences, and the green is all the savings. So this is electricity savings, and then down here is the gas savings. Implemented right here, again, 50% savings in gas. So electricity savings is not quite as dramatic because you got all the lights and plugs that sort of drown out the HVAC in terms of percents. But it's big numbers. And it's really, I mean, to me, this is really, we talk about putting in heat recovery and we're doing this and doing that. Hey, this is better than that all by itself, and it's damn near free. So what's next? We're just finishing a research project on sequences of operations for hot water and chill water plants. So this will be optimized sequences for those. That will fill in a whole bunch of missing stuff that we have now. Should be into Guideline 36 before the end of the year. Then we have RP 1865 on sequences for DOAS systems, for dedicated outside air systems. One of the things that people don't realize, they think, oh, DOAS, that makes all the reheat energy like goes away. We don't have reheat because it's a DOAS system. It doesn't work that way. If you're doing any conditioning of the air at the DOAS, then you will have reheat or recool, because the supplier temperature is only going to be right for one zone. All the rest of them is wrong. And so you're going to be, the zone system is going to be fighting, and so we need to figure out how to do that in an optimal fashion, which gets pretty complicated if you have a whole bunch of heat wheels in there and all that kind of stuff. So that's just was issued, and we're actually going after that one to bid it with the UC Berkeley guys again. And then we have all sorts of addenda on the horizon. We have one that we're about to issue on laboratory VAV controls. So traditionally, laboratories have the controls done by the air valve guy, the Phoenixes and the AccuValve and those kind of guys, because they have their own proprietary system. But then you end up with two systems in the laboratory, one for airflow control and one for temperature control. Well, this puts it all in the building automation system, so we don't need those guys anymore, and you can do everything with the lab controls, so it can be less expensive and work better. We don't have any heat energy wheels or heat wheels in the logic right now. We have an addendum working on for that, and a whole bunch of bug fixes. So as people are using these things, of course, we got it wrong. Although most of these sequences we've done before, and you always find something that can be done better. So that's where we are. All right, conclusions. Guideline 36 combines the best of the configurable and programmable worlds. We get plug and play, but we get advanced sequences at the same time. The long term, the engineers don't have to write any of their sequences. Sequences are pre-programmed and debugged already by the controls manufacturer. We have, because of this project with California, we have two manufacturers. I guess I can say commercial names here, right? There's no ASHRAE kind of thing. So ALC, Automated Logic, has got almost all of them done. Not everybody's doing all of them because, like I said, there's 5 versions of dual duct, and not that many people use dual duct, so a lot of them are shining off on the dual ducts. And Distech has them in there. So those two. And locally, we have a dealer who's done our sequences for Allerton, as well, but so far they haven't been willing to share it with any other dealers. They put a lot of money into it, and they're not going to share it. And then, so we're at, okay. And then, yeah, the controls contractors no longer have to program the sequences; they're already being programmed, and the commissioning agents no longer have to test it. It's totally a win-win-win for everybody. We just need to get the ball rolling, and getting the ball rolling is by getting engineers and your techs and everything to work with them. All right, so that's that. Any questions? Yes?
Fantastic. So you were talking about the dual max. So the dual max, when you were stating that, I understand trim and respond coming down with the static. But the spaces, you mentioned the labor's task of finding the worst case box, 99.9% open or 100% open, but 99.99 still under control. And that's what really drives your static pressure set point for a building. But then you made mention you don't have to do that. Trim and respond. Are you saying trim and respond on the way up? Because then we got static pressure cutouts that may occur, right?
Well, the trim and respond is based on request. So a zone that needs more static, when their damper's almost all the way open, will say, I want more static. And the zones that are down lower, they're not going to generate any requests at all. So they're perfectly happy. And so only the ones that are the critical zones are going to have requests. But if you saw from that screenshot I have, which is a real job, the number of requesters was almost every zone at some point in the day. The sun's over here, these guys are requesting. The sun's over there, those guys are requesting. When in the wintertime, it's the interior zones that are requesting. So it spreads itself around.
No, I understand it. Your diversity. So as the load changes. So on the way up, static pressure set point, and the box, let's just say it's an undersized box for just making this conversation be correct. It's an undersized box. It's never going to have enough static to deliver to that space. Can it still, I'm just asking, is your theory here, design, can we still drive and take the static?
Too high? No.
Yes.
So I didn't put it on here, but I should have. There's a table of all the parameters for the
Okay.
trim and respond.
That's-
One of them is maximum set point.
Okay.
I'm never going to go above that. And we still like people to determine that the old-fashioned way.
Worst case box.
You basically, all the boxes downstream of the static pressure sensor, you make them go to design, and you see what pressure you need to make them all happy. And that used to be a fixed set point. And now it's the maximum set point. And
Now
so
it makes
you
sense.
can't be worse than conventional.
Okay, that
Yeah.
makes sense.
Yeah.
And one thing, because really you're educating them that they need to work with the balancers, and you have obviously a balance contractor that gave you real data. He was a real balance contractor. And that's really where you'll lose it, is the drive-by balancers.
Yeah. Well, we're getting in our own specs, and so Guideline 36 is just sequences, and it's not going to tell you how to start the building or whatever. It doesn't have any test and balance requirements. At the very beginning of it, it has a section of set points that are determined by others, and it will say maximum static pressure is determined by others, but and it has a little blurb in there about how you might do that, but it's just a set point to the sequences. It doesn't know. In our own jobs, balancers, they're not terribly reliable people, and in my experience, and so we now are moving all that into the realm of the controls guy, because think about this: I need to determine that static pressure set point. I don't have to go out in the field at all, right? I can just command the boxes from my terminal, just make those boxes go to design cooling, and I just keep lowering that set point until I start starving a zone. I can do that all from my computer. I don't have to have any balancer at all. And I don't care if it's 1.1 inches or 8.1 inches. It doesn't matter. I'm resetting it, so it doesn't even have to be accurate. It's just it's ohms. It doesn't matter what it is. It's not a physical thing anymore because I'm resetting it. So you can do almost all this stuff without balancers at all. So we've written our specs that put a lot of that work that's traditionally balancer work and just made it the controls. And the reason we got there is because we were doing that as part of our commissioning tests. We would see, hey, did you set that set point right? So we had a test to see if they set the set point right, and we said, why don't we just do that to determine the set point, and save everybody the trouble.
And the last comment I'll have, which we agree, enthalpy and humidity sensors, huge issue. If they last a year accurate, you hit a home run. What we did in our lab for the people building their labs, what we did to know when you're wrong, enthalpy-wise, expensive now, the expensive route to go. But what we did was, and it came from Dr. Jamie Wixer, and he's the one who puts the sensors up on the Mars rover, and he does 3. He puts 3 enthalpy sensors, dry bulb, wet bulb, and then you're just watching for one sensor to go astray. That's when you can properly assume you're out of calibration with that one, because 2 still look alike, 1 goes stray, and that's just the thought, and that's how we control accuracy.
Right. In our jobs, we try to avoid needing humidity sensors. And one of the cases where we always need one is we do data centers, and we have waterside economizers. And when you have a waterside economizer, you need to know the wet bulb temperature to enable the waterside economizer. So we need outside air humidity. What we use is a high quality dew point sensor. It's actually got dry bulb and relative humidity, and then it combines it to dew point and wet bulb. You can get any psychrometric thing you want out of it. But what we do on that one is that we get dew point out of it, and we look at the nearest NOAA site, the National Oceanographic, whatever it stands for, and they have super calibrated sensors that are getting accurate data. Well, the dew point, dry bulb and relative humidity go all over the place, but dew point is pretty constant for a broad range of space. So you find the lowest, and then you connect into it with your DDC system. And you just download their sensor every hour or so, and you compare it to your sensor. And when they get too out of whack, you make an alarm go. Now that only works with outside air, of course,
Right.
but in the case of our water side economizer, that's all we need. When we do, we just did the San Francisco Museum of Modern Art, and on that one, it's very tight humidity. And so we just make it so that the air is saturated coming off the cooling coil all the time, either with the cooling coil itself or with basically a direct evaporative humidifier, direct evaporative cooler. The air is always coming off at 52.5 near saturation, and that puts it right in the space automatically. So we don't even have to measure humidity at the zone level. We do because they need it for to prove that they're maintaining their humidity. But we don't have to. It actually maintains it by itself. So we do what we can psychrometrically to just avoid humidity sensors.
Then,
And by the way, on the economizer one, in the study that we did that came up with all these set points, you can get it off our website. It says, it's why enthalpy economizers don't work, is the name of the article. And in that, we did all these simulations and showed that, the dry bulb ones, if you get the set point right, they work almost as well as the differential enthalpy anyway, within a couple of percent. And that's if the enthalpy ones actually worked, which they don't. And so it's really, there's not too many reasons to use a humidity sensor.
I'll throw it out there. We like Vizsla. What do you consider high quality? What are you using when you say
The
high quality?
Vizsla.
You use
Yeah.
Vizsla? That's what we figure are the best too.
Yeah, and it's reasonably priced too.
Right.
Yeah.
Okay,
and
we're on the same page.
it's by far the best. Yeah, Iowa State did a study on humidity sensors, and it was definitely the best.
Yeah, their
all.
drift is like 2 years.
Yeah.
Where
It's-
everyone else is worse.
Yeah, and since if you're only buying a couple of them, it's absolutely worth the money to get theirs. Yeah. Yeah.
I guess we've grown so much that we got away from Benjamin Franklin, the slinks are common. Because I remember the days some of my students that went on to engineering jobs, and they went up and, okay, I think we're getting away from maybe just basic science. Benjamin Franklin, the sling psychrometer. Because I remember as my students leave and they go on, I have a reference, one of my students worked for an engineer at McNay Arts Institute up here in San Antonio, and wherever they got special guests or when they got the skeletons in, as they come in and have all arts and they bring different things, they have to set the humidity. So they would, at certain times, with a sling psychrometer, go into and measure it. It says that's how we make sure that's correct. So sometimes we just got to go back to basics.
Yeah. Yeah. Another comment in that same regard. I have this little Ecobee thermostat in my house, and it has humidity in it, and I know it's got to be a cheap sensor. I mean, the whole thing costs $120, right? It can't be a very expensive sensor. So I contacted them and asked for some support. And it's basically a solid state humidity sensor. I'm not even sure exactly what the technology is, but the good ones are going to be a capacitance type or something. But they're flawed when it comes from they have to be calibrated. So maybe and of course this guy told me this thing was probably plus or minus 10%. Which in a little thermostat in your house, I don't even need the thing, but it was there. That's probably good enough. But it's solid state, so it never changes. And it's like maybe we're doing this wrong. If you don't really need to be precise, let's get a cheaper one that always stays calibrated, because that's better than one that's super accurate but is always out of calibration. Garbage in is worse than inaccuracy. So yeah, probably other things we can do.